All right, 8.2, the Cartesian equation of a line into space. So we have 5 different forms we're going to present it. So here's our first form, y equals mx plus b. Our second form, our third form, fourth form, and our fifth form. So all of these forms right here that you see here represent different forms of an equation of a line. The first form is the one you were introduced to in grade 9. That is known as the slope-intercept form. The next form over here is one we just learned in the previous section, which is the vector equation of a line. The next form is also one we just saw, and it's known as the parametric equation. This one is the standard form of an equation of a line, which is also known as the Cartesian equation. And we use that when we have this. We use this form that we have over here to be able to solve it and get this. And finally, the last form over here turns out to be our symmetric equation. Now, our symmetric equations are basically when isolated for t. All of these values will actually equal your parameters. So now, we're going to look at an example. Given the vector form of an equation, and what you have to do with that vector form is state the Cartesian equation of that line, the parametric equation of the line, and the symmetric equation of the line. So we're going to go through different forms. The easiest one is, let's do the parametric from the vector form. Vector equation, to make the parametric equation, we just isolate for the individual variables. So x equals 5 plus 7t. Y equals -1 plus 2t. So next part we're going to do is the symmetric equations. The symmetric equations are basically isolate for t by subtracting 5 and then dividing by 7. And also for the next one, y plus 1 divided by 2. And that will be your t value. Next, we're going to look at the Cartesian equation. Now, we can do it the old grade 9 way, which is exactly as you see here. And we plug it into the equation that's more convenient at the grade 12 level. And we plug it in, multiply the side by 7, so that we can get rid of that fraction and move everything so that the x is positive. Now, another way that you could have gotten this particular Cartesian equation is by using the symmetric equation and cross-multiplying. Because if I cross-multiplied and took 2 times x minus 5, guess what? That will give us 2x minus 10. 7 times y plus 1 will give us 7y plus 7. So yes, folks, we can cross-multiply the symmetric equations and we will get the Cartesian equation. Cool, eh? All right, let's moving forwards. Let's move on. Here's a question. Does the symmetric equation of the line always exist? So remember that the symmetric equation has something on the bottom. What is on the bottom? Does that value always exist? Well, folks, let's look at the symmetric equation. Remember that these are part of the value next to t, and you divide by it. Could there be a possibility where it doesn't exist? And yes, there is. So ultimately, the symmetric equation of the line doesn't always exist. No, it doesn't always exist, because if the line is horizontal or vertical, then that's when the direction vector will have a 0 involved. So that will happen when the direction vector is either horizontal or vertical. This particular these type of equations, symmetric equations, actually don't exist. Interesting. Another part to note. The Cartesian equation actually has a special relationship with the line. The Cartesian equation actually contains the normal. The vector AB, so the value next to x would be your A, and the value next to B would be your B. That AB vector is actually the normal vector. The normal vector is a vector perpendicular to the line. And so AB is our normal vector. And it's interesting. We're going to find out why that's the case. So let's look at the equation. If we were to isolate this Cartesian equation, isolate for y, you would have y equals negative ax minus c, and then you would have to divide by b. So negative a over b, x minus c over b. So what would happen is that this part right here is our slope. That slope is delta y over delta x. So if we were to write this as a direction vector, it would be b delta x, comma, delta y, which is negative a. So b negative a. And what we're going to find out is that in order to make it perpendicular, it would be the flip and change the sign. So our regular vector, our normal vector is AB. But what is our regular vector? Our regular direction vector. Our regular direction vector M is going to be delta x, which is b or negative b, a. Or you could rewrite it as b negative a. Ultimately, that is our direction vector. So our direction vector starts off like this. But when you convert it to Cartesian equation, funny enough, the Cartesian equation coefficients of x and y turn out to be our normal vector, which we use n to represent our normal vector. Cool. All right, let's go on to another example. So example 2. Given the normal, 6, negative 7, and the point 1, negative 2, state the equation of the line in Cartesian form. So this time I give you the normal, and I give you a point. So if the normal is 6, negative 7, then the direction vector is 7, 6. Why? Because don't forget the x and the y change, and the sign changes of the whole normal vector. So if it's 6, negative 7, it's going to turn into 7, 6. And so what we can do with this is getting the regular, that's right, the regular slope, which is 6 over 7, and the point, we can plug it into the equation. Why do we need to plug it in the equation? Well, what we need here, folks, is our Cartesian equation in such a way that we can find the values. So our Cartesian equation, you multiply both sides by 7, expand it out, and collect like terms. And this, folks, look here, that's our normal 6, good, negative 7, good, and we can find that c value that we're missing. Another way we could have done this, had we approached this question a different way, is I could have approached it in a different way by doing the following. I could have said sub, and that's right, we could have subbed 6, 7, so it's 6, negative 7 for A and B, and we could have subbed the point for 1, negative 2 for x and y, and we could have gotten our equation that way because we're only missing our c value for Cartesian equation. So A would have been 6, x would have been 1, plus b, which is negative 7, times y, which is negative 2, plus c equals 0. And that would have given us 6 plus 14, which is 20, plus c equals 0. That means c is equal to negative 20. And so our final equation would have been exactly the same over here. Our A is 6, our B is -7, and our C is going to be -20. So one way you did it using the way you learned in grade 9, and the other way is using our knowledge about A and B, which we just learned earlier, that A and B are our normal vectors to the line. Cool, eh? So the Cartesian equation is 6x minus 7y minus 20 equals 0. All right, example 3. So, for what values of k will kx plus 3y minus 6 equal 0 and 5x minus 8y plus 7 equal 0 be perpendicular? So, for what values will these two functions be perpendicular? What do you know about two perpendicular lines? Well, I know that they're direction vectors. The dot product of their direction vectors is equal to 0. So, if I know the direction vector of one of them, and I know the direction vector of the other, that we can take the dot product for. So, you can find the direction vectors for each of these lines. The other thing to note is that this is the normal of this line, and this is the normal of this line. If these two lines are perpendicular, then their normals will also be perpendicular. So we could even approach it that way. So let's solve this problem for one way by finding, for example, there's our normal vector. Oh no, sorry, that's our direction vector. It is the normal vector to this is k3. Our direction vector will be the perpendicular vector of k3, which is -3k. And for the other one, we also find the direction vector of that one, which is 8, 5. Remember, again, it's b negative a, or negative ba, however you choose for it to be. And then we take m1 times m2, or dot m2, and we set it equal to 0. And we take the direction vectors and set them equal to 0, the dot product of those direction vectors. We find out that k is equal to 24 over 5. Now note, these direction vectors I'm going to show you here are all possible direction vectors that you could use. Why are all these the same direction vector? Well, because don't forget that a direction vector multiplied by the scalar is still the same direction vector. Think about when you have a fraction for a slope. If you reduce that fraction, it is still the same slope fraction, regardless of whether it's reduced or not. So I want to try this experiment. Could we have gotten the answer had I multiplied the normal vectors? Would I have gotten the same answer? Why not? Let's try that experiment. Okay, so looking at this, we're going to use the normal vectors. So I'm going to erase all of this right now. And we're going to try and use the normal vectors for this, okay? So how we're going to do this is take the dot product of the normals. To do that, we need to find the normals. So the first normal is k3. The second normal is 5, -8. We set the dot product equal to 0. We calculate the dot product. Remember that the dot product is k times 5 plus 3 times -8. And that's how we got 5k minus 24 equals 0. That's how we got there. So that means 5k is equal to 24. That means that k is equal to 24 over 5. And guess what, folks? We got the same k value. Okay? And it's interesting how we got the same k value for what we were looking for earlier. So whether we take the dot product of the regular direction vector or we take the dot product of the normals, we'll still find this same k value. Interesting. All right, moving forwards. Next example, example 4. If you're given two lines in the symmetric form, and you're asked to find the point of intersection and the angle between them. That's what you're asked to find. So, let's look at them. We take 10 times L1 so that we no longer have a denominator, and then we also look at 5 times L2 so that we no longer have a denominator. We can now set equations 1 and 2, and we can add 1 and 2 together so that we get just the x value. So when I add, I'm going to add negative 2x plus x, and that gives us negative x. I'm adding this, that gives us 0. Adding this, that gives us 0. And adding this, and that gives us negative 5. So we have negative x equals negative 5, x equals 5. Once I find that x equals 5, I can sub it in equation number 2, and I get, in equation number 2, I get the y value equals negative 2. So my point of intersection is going to be 5, negative 2. So we can use this form to find our values, okay? But we're not done yet. We need to find the angle between line 1 and line 2. The way we do that is we can take the dot product, because the dot product is equal to the product of the magnitudes times cosine of the angle that is between them. So, take the dot product of A and B. Well, A has the direction vector 5, negative 2. B has the direction vector 5, 1. And then we take the magnitude of each of these vectors, individual vectors. That would be root 29 and root 26 times cosine of theta. We isolate for cos theta, so we get root 29 over root 29 and root 26 on the bottom, and on the top is the dot product of the two direction vectors, and that would be negative 27. Take the cos inverse of that value, and we find out that the cos inverse of that value will give us an angle of 169.5 degrees. So the angle between the two lines is 169.5 degrees. The acute angle between them would be 10.5 degrees. So either the very large angle of 169.5 or the acute angle is the opposite angle. So one of those two angles is the angle between the two lines. All right, that's the end of the video, folks. Have a numerical day.